So let's try to solve this initial value problem given by y double prime minus 6y prime plus 9y is equal to t squared e to 3t, where y of 0 equals 2 and y prime of 0 equals 17. And again, this is the type of problem that we could solve last exam using constant coefficients and undetermined coefficients. And we're going to go ahead and compute Laplace of both sides so that we're able to find Laplace of the left and set it equal to Laplace of the right. And I'm trying to leave this space up here blank so that I can write the Laplace properties we need as we go. So for the left side, I'm computing L of y double prime minus 6y prime plus 9y. From linearity, that's going to be L of y double prime minus 6 L of y prime plus 9 L of y, which is going to be my s squared y minus s y of 0 minus y prime of 0, following that derivative rule, minus 6 times sy minus y of 0 plus 9 capital Y. I'm going to plug in my numbers and then distribute, I think, because 2 and 17 are pretty big numbers. So I've got s squared y minus s times 2 minus 17 minus 6 times sy minus 2 plus 9y. So that's going to be s squared y minus 2s minus 17. Then distributing my minus 6, I've got minus 6sy. And remember, when I multiply this all the way through, I'm going to get plus 12. Please be careful of things like that. Plus 9y. And I'd like to isolate y, so that's going to be y times s squared minus 6s plus 9 for all my y terms. And then everything else left outside, minus 2s minus 17 plus 12. Or simplifying everything as much as possible, I'm going to have s squared minus 6s plus 9 is just s minus 3 squared times y, minus 2s minus 5. Yeah. And then taking Laplace of the right side, I'm going to look at Laplace of t squared e to 3t. And I think in the order that we work with it, we're used to seeing the e up front, but now it looks like that property we just learned, L of e to ATF is equal to big F of s minus a. And in this case, we are thinking about a being 3, and that big F being L of t squared, which is going to be s to power 2 plus 1 with 2 factorial on top. So that's just 2 over s cubed. It's a bad 3, but I'm not going to erase it. So when we apply our property, we're going to get f of s minus a, so f of s minus 3. So we're just going to take this, which was big F, and then plug in s minus 3 everywhere we see s. So it's going to become 2 over s minus 3 cubed. And at this point, we've taken Laplace of both sides, and we can go ahead and set them equal and start solving for y. I need to move to the next slide to do that, so go ahead and take a second to pause if you need a bit more time here. But when I set both sides equal, I'm going to get s minus 3 squared times y minus 2s minus 5 is equal to 2 over s minus 3 cubed. Or y is equal to, I move 2s plus 5 over, so I add my 2s and my 5 on the other side. And I already had that 2 over s minus 3 cubed. But I divide everything by s minus 3 squared to isolate y. So that s minus 3 cubed actually becomes an s minus 3 to the 5th power. Since you can add together powers when you're dividing them or multiplying them. So then, if I take inverse Laplace of both sides, I'm going to get little y on the left all the time. And then I just need to find L inverse of 2s plus 5 over s minus 3 squared plus 2 over s minus 3 to the 5th. And if I can do that, I'll be done with this problem. Since I see s minus 3's, I need everything to look like s minus 3. Or another way to remember it is if you use this property when you start your problem, you're probably going to have to use the opposite when you return, so you need to put everything in terms of s minus a. Either way, I end up finding that my 2 over s minus 3 to the 5th term is already okay. But then this one, we have to manipulate kind of like our other example of taking an inverse. So I'm going to need 2 times s minus 3 instead of just 2 times s squared. That's 2s minus 6. Remember what we said, to make that plus 5, we're going to have to balance it out with a plus 11. So by linearity, this all becomes 2 L inverse of 1 over s minus 3 to the 5th plus 2 L inverse of s minus 3 over s minus 3 squared plus 11 L inverse of 1 over s minus 3 squared. And for all of these, we're thinking about a equal to 3 to have that s minus a, s minus 3 term. And then I'm going to give myself a little bit of space to kind of take notes about how I'm taking my inverses. What can be helpful once we start getting these really complicated inverses is filling in anything we do know. So this middle term is my easiest term. When I simplify it, I just get that this is 1 over s minus 3. That's one of those exponential terms. So I would go ahead and fill that in right away, just so that I have the answer in case I can't get the rest. And then for my other two, I do have to use our new property. So for this first one, I'm looking at something that looks like s to the power 5 on bottom, which means it would have 4 factorial on top. And that corresponds to my little f being t to the power 4. And for my rightmost term over here, I'm looking at a big F that looks like something with s squared on bottom, which means it would have 1 factorial on top, and my little f is just t. So then, for this term, I need it to be 4 factorial over s minus 3 to the 5th, which means I need to divide by 4 factorial to balance it out. In this term, I don't have to correct because 1 factorial is 1, so it's fine the way it is. It's just 1 factorial over s minus 3 squared. Now I can go ahead and plug in that e to at times f property. So this becomes e to 3t times my f, which is t to the 4th. My middle term is unchanged. And again, for this a, we have e to 3t, and my little f was t. Simplifying a little bit, I guess, I've got 2 over 4 times 3 times 2, so that's just 1 over 4 times 3, so 1 over 12 t to the 4th e to 3t plus 2 e to 3t plus 11t e to 3t. And that's our solution for y. So that's a solution you could have gotten a different way previously, but we just learned how to do it with Laplace. And in our next video, we will move on to working with that curly u function that we introduced earlier.